Muchas gracias por estar aquí en este seminario institucional extraordinario, donde tenemos el gusto de oír a la doctora Ioana Voiculescu del City College of New York. Ella tiene 2 doctorados, el primer doctorado en ingeniería mecánica lo sacó de la Universidad Técnica de Timișoara en Rumanía y el segundo de la Universidad George Washington en Washington, D.C., también en ingeniería mecánica. Ha sido receptora de varios proyectos, especialmente de la National Science Foundation y de la Oficina para Investigación Científica del Ejército de los Estados Unidos, donde ha trabajado en sensores para varias aplicaciones, químicas, biomédicas, etcétera. Trabajó también un par de años en los laboratorios de investigación de la Naval de Estados Unidos, donde desarrolló especialmente sensores para explosivos y para agentes químicos precursores de explosivos. Tiene más de 30 artículos en revistas científicas internacionales y publicó un libro sobre las vigas de trampolín que se usan en MEMS para muchas aplicaciones de sensores. Trabaja mucho en sistemas microelectromecánicos, especialmente combinados con sistemas CMOS, con circuitería CMOS, en lo que hoy en día ya conocemos como laboratorio en chip. Entonces, sin más, les dejo a la doctora. Thank you very much.
Thank you very much for the nice presentation, and I hope you will understand my English. These are 2 sensors I developed in my own research laboratory. The professor explained that I was working for Navy Research Laboratory in Washington, D.C. for trampoline cantilever beam. That was an interesting research, but I do not present. That is my PhD research. This is the research I did in my lab with my PhD student. So I'm Ioana Voiculescu, and the university is called City College of New York, and it's part of City University of New York. It's a very huge conglomerate of 24 universities. And I'm very grateful because I was in the PhD program at George Washington University with the professor José Luis Rebollar Hernandez, and he invited me for this presentation, and I didn't see him in 17 years. By the time we departed, I came to City College of New York from Washington, D.C., and he returned to Mexico. So I want to present 2 sensors. In America, in United States, for me to get money for my research, I needed to understand to do research in biotechnology. When I started, because my previous research was with explosives and chemical sensors, it was nothing connected to biotechnology. When I started, I realized I cannot get research money, and then I developed these topics, this type of research. First topic, you see 2 different topics of 2 different subjects, and my presentation is about 40 minutes, 45 minutes. It's not a long presentation. First topic is MEMS microelectromechanical system biosensor with integrated impedance spectroscopy and gravimetric measurements for water toxicity testing. My second topic is wearable and stretchable piezoelectric power generator. So a little bit we start the first topic and a little bit of the motivation for this first topic of MEMS biosensor with integrated impedance spectroscopy and gravimetric measurements for water toxicity testing. So I wanted to get money for my research from Army Department. And so I wanted to come with this is my own idea, some idea which is good for the soldier in the field, going to strange exotic countries. And so is a sensor which is based on mammalian cells, live mammalian cells, biosensor. So the sensing layer are these like live mammalian cells, and it is used for monitoring the water toxicity. So what is the idea? Very simple. You put water on the mammalian cells and you see if the cells are dead or alive. If the cells are dead, that means the water has some toxicant. It's a very long process to find out for the soldier what is in the water. So this sensor will not tell us what is in the water. It's telling us, oh, the water is not good. Please be careful. Don't use the water. This is it. More than this, you don't know. And when I conceived this idea, I wanted to integrate two sensors because I was thinking one sensor is not enough, and two sensors which are testing the same thing. Are the cells alive or are the cells dead? So we don't use the microscope. We just put water on the sensor, and then monitoring the sensor response. We see the cells are dead, the cells are alive, and we have two sensors which will tell us the same information. One sensor, so the sensors are impedance spectroscopy integrated with gravimetric sensing on a single chip. The impedance spectroscopy is called electrical cell-substrate impedance sensing, ECIS. We say ECIS to this technique for testing the cell viability. And the second, the gravimetric sensing, is in fact a quartz crystal microbalance, resonator for testing, both are for testing the cell viability. Now, the cells are bovine aortic endothelial cells, and from testing the water toxicity, we didn't use very dangerous toxicant because I do in my lab, I don't want to be in the atmosphere of very dangerous. We use this toxicant which are generally in the insecticides, and they can come into the water when they spray the toxic on the culture of some vegetables or something like ammonia, nicotine, aldicarb. We use to test our sensor as toxicant. Also, if you have questions, you can maybe stop me for question, or you can remember your question till the end of the presentation, you know. I try to explain the details because I know maybe not many people are in this field of biotechnology, but I think it's an interesting topic. So, what was my motivation? I got inspiration, you know, we all got our inspiration from conferences, from journal paper. I will not come like this come to my mind like that out of the blue. So I read a paper and the army had the sensor already. The sensor was very big and was based only on impedance spectroscopy technique. So I was thinking, why not to have two techniques to be more sure? So here is the current cell-based biosensor, has large size and uses only one type of sensing for monitoring the cell viability, which was the impedance sensing, ECIS. We say ECIS. And this was developed many years by Army. Our goal was to create a portable device that will include a smaller chip that will require a small number of cells. So for their device, they need a lot of cells. I wanted my device to have less cells. And also the combination of two sensors will provide higher detection accuracy and lower false positive rate. Okay. Now I will explain a little bit the sensor, because the first sensor is electrochemistry, so people from chemical engineering are a little bit more familiar, but it's electrochemistry, so also, so the first one, this one is electrochemistry, the ECIS sensing method will detect the dielectric properties of cell membrane on the working electrode. So for ECIS, you need a working electrode and you need an electrolyte, which is the cell media, and you need a small alternative current voltage, which is applied between the working and counter electrode, and the change in impedance is measured as the current flows through the cell culture medium as electrolyte. When impedance values reach 0, the cells are affected by toxicant and are apoptotic. Apoptotic means dead. Here, what we do, if the cells are alive, their membrane have high dielectric properties. So with this technique, we constantly measure these dielectric properties of the cell membrane. When they are dead, of course, they don't have that dielectric properties, and then we see our impedance is dropping to 0. The second technique is the quartz crystal. It's a resonator. Both are sensors. This is a resonator. This is very common resonator, where you use quartz substrate and 2 gold electrodes are fabricated on the opposite surface of an 80 cut quartz substrate, and you produce acoustic wave inside, named thickness shear mode acoustic wave, and you measure the resonant frequency. And when the cells are attached to the quartz crystal, the resonant frequency has a value. When the cells are dead, they detach, the sensor is much lighter, and the resonant frequency is increasing. So this is the idea of the both sensors. Now, here is the quartz crystal with the impedance spectroscopy. This is a sketch of my idea, and we can see a combination of 2 sensors. So first, let's look at the quartz crystal microbalance, which is a very common device, very well known, very developed. It has the quartz substrate, has the upper QCM quartz crystal microbalance electrode. You need 2 electrodes to produce the acoustic wave, and the acoustic wave looks like that inside the quartz substrate. If the cells are attached, the resonant frequency has a value. When the cells are dead, they detach. And this is like a microbalance, is lighter, and the resonant frequency is increasing a little bit. Now, the second sensor is this ECIS, electrical impedance spectroscopy, which is a chemical sensor, electrochemical sensor. It has 1 electrode, which is the working electrode, and which is also the electrode of the quartz crystal microbalance. So we culture the cells here, and it has a second electrode, and using the 2 electrodes, you measure the impedance of the cell membrane. Of course, it's a little bit an approximation, because it's a function of how many cells you have there. It's very hard to count the cells with high precision. But the idea is good for the scope of checking the water quality. If the water is okay, the cells are alive. If the water is toxic, the cells will die. This is the idea. Now, in this impedance spectroscopy technique, a current is applied through culture cells attached on gold electrodes. The cells attach this. I didn't know how to work with live cells, but I wanted my student, so I learned. I wanted my PhD student to work himself, not to find a biologist. So he can do his experiments when he has time. You need to wait. It's very laborious. You need to wait till the cells attach, because you put the cell there on the sensor, but they will not attach in the first moment. You need to wait a time to attach. Then the cells are spreading, and then they form a very nice monolayer. Meanwhile, the impedance increases because the cells act as insulating particles and restrict the current flow. Now, the impedance values can be continuously monitored and interpreted to reveal information about cell micromotions, cell spreading, growing, attachment, and what is important for us, viability. This is the most important information for toxicity studies. And I have here a sketch. I think this sketch is very good to understand the technique of impedance spectroscopy. You have 2 electrodes, and you apply a pulse between the electrodes. You create an electric field, And the electric field will go through the cell junction, which are very, very small at nanometer scale. So the cells are a little bit blocking the flow of the current. And the impedance values when the cells looks like monolayer are high impedance values. And for this electrochemistry, you need at least 2 electrodes. Here is the fabricated sensor. Now I have a small clean room, and the sensor is a little bit primitive with like large dimensions. You know, in MEMS, the dimensions are very small, micro scale here. I didn't put the dimensions, but this one is 1 millimeter, this one is 1 millimeter. So the dimensions are almost in millimeter, not in micrometer. So because it's easy to fabricate, you don't need a mask like a sophisticated mask. You print the mask with the printer when you do this type of fabrication. So here is the top surface, and this is the combination of the 2 sensors. Here we have 1, 2, 3, 4 sensors. The substrate is quartz crystal, and then you have what you can see here is the top electrode of the quartz crystal microbalance, which is also the working electrode for impedance spectroscopy. Impedance spectroscopy requires 2 electrodes. This is the second electrode, which is called a counter electrode. So we culture the cell in this area. And then we fabricate it. It's not so clear in this slide, but you can see in the next slide, you need to fabricate cell culturing chambers. It's a technique from PDMS, very well-known technique how to fabricate microfluidic channels in PDMS. So we fabricate some culture. Maybe this is 1 centimeter, 1 centimeter. So here we have 2 centimeter per 2 centimeters, and the connections. And we are mechanical engineers, so the student did this printed circuit board. Probably he could do better, but this is what we were able to do. Now, if you know the MEMS technique, I will explain a little bit the fabrication steps of this sensor. So it's very simple because, as I said, my lab is not so sophisticated, and the student cannot do very small dimensions of devices because the whole fabrication is based on lift-off technique. For lift-off technique, you use the quartz crystal substrate, and you use the photoresist. And generally, for the lift-off technique, you use AZ photoresist, which is an image reversal photoresist, and you use UV light. You use the mask. As I told you, we print the mask with the printer, black and white. We didn't buy, like a regular mask. Our mask with the printer may be $50. The regular mask will be like $450, the one on the glass, the plastic MEMS mask. And then we deposit a very thin layer of chromium and gold, one on top of the other, and then we remove the photoresist. This is the classic lift-off process, and what we get was the quartz and the electrodes, and then we turn the quartz crystal and we pattern the back electrode on the back for the quartz crystal microbalance. I will not enter into the fabrication protocol because it's the protocol which corresponds to AZ photoresist, image reversal photoresist, which is a positive photoresist, but it's transformed into negative photoresist by doing these steps here. I show you now the culturing. This is a little bit sophisticated. We needed some time to be able to do the culturing chambers. Here it looks like it is open, but now the top layer is closed. So the cells are not exposed to air, even the air in the incubator. The cells are in a enclosed, yeah, you can see here. Here is the chamber of the cells, and here is one you put one tube to introduce the cells and the cell media. Here is another tube to extract the media, which was already used by the cells. We use PDMS. Absolutely the classic PDMS microfluidic fabrication. Again, for this fabrication, you also use mask, and you can print the mask with the printer, because the microchannel dimension was 80 micrometer per 80 micrometer. What is happening with this cell culture? You need to create a laminar flow. Like the flow has to be very uniform. That is the reason we complicated a little bit our fabrication with this so-called perfusion chambers. So perfusion channels. So the media comes very uniform. If the media is not coming uniform, will disturb the cell monolayer. And we don't like to disturb the cells inside the culturing chambers. And we use PDMS, and we use SU8, and we use 2 layers. We fabricate 1 layer of PDMS, which contains only these cell culturing chambers. And then the second layer contains this structure of the microfluidic channels. And we put this on top on our chip. This, what you see here, are the cell culturing chambers on the fabricated chip before connecting the chip to the printed circuit board. I think I will not explain you all the details. It's very laborious. If you do biotechnology experiments, you need to have everything very clean. You need to autoclave. We put some deionized water and autoclave to make sure the inside where you will put the cells is very clean. The cells were bovine artery endothelial cells from bovine for a huge mammalian animal. The cells are bought from a company. I don't cut in the artery and extract the cells. I'm not at that level, you know. I'm like buying the cell line and just culturing on I knew how to culture the cell on my device by my student, not me, but I managed to train him, and he did the fabrication, he did everything. And this was his PhD work. He was a very good student. I was very lucky. I was thinking he is not so great. But after he graduated, comparing to other students, he was very, very good student. It's very hard I think, to be a PhD student, because you need to dedicate all your time to your idea. You know how it is. Anyway, let's come back to the presentation. So here is the sketch. Here I want to show you the instruments I'm using for my measurements. Maybe I can use other instruments. I don't know. I'm, like, as I said, mechanical engineer, and these instruments were simple for me to use, and I have in my lab. So for the impedance measurement, you need an impedance analyzer to connect the 2 electrodes at the impedance analyzer. And for the resonant frequency of the quartz crystal microbalance, you need a network analyzer. So you need these 2 devices. And yeah, here you can see upper QCM electrode, which is also the working electrode for the impedance spectroscopy, and the counter electrode here. And I also show you a picture from my lab. You need also an incubator to do this type of research, because the cells has to stay constantly, the sensor is inside in the incubator at 37 degrees Celsius, and the cells need to survive. To have oxygen in the incubator, you need to introduce CO2. This is network analyzer, this is impedance analyzer, and he wrote a LabVIEW program for this research. And what is here is the resonant frequency. A quartz crystal microbalance does not have high resonant frequency. the maximum resonant frequency around 1652 megahertz, and then using COM-SOL, he simulate. This is very simple simulation. This is really simple simulation. So he managed to get, and it's based on the thickness of the quartz crystal, the substrate. And then we look at the cells. This is very important. The cells are attaching very strongly to the substrate, and then they are very stable for a long time. I have another paper. We monitor the cell around 30 days, and they didn't die. They a little bit increase the impedance because they proliferate, but sort of not dying, because the army wanted a cell not to die. Why the cell has to be have a bit of long life? Because the soldier is taking the device with the cell. The soldier will not culture himself the cell on top of the device, so he will have the device in a small incubator, and the cells has to resist about 20 days or 15 days till he arrives somewhere and wants to taste the water quality. And this is the way the cells are looking. In the third day of, see how laborious is. You cannot do the testing immediately. You need to wait at least 3 days till you form a monolayer of the cells, and then you can start to, this is the 10th day, anyway, the 22nd day, the 30, and then the cells are dying after like 30 days. They are not happy. This type of cells. Later, I don't know if it's an important information or not, but later the army switched to the fish cell, because the fish is cold, doesn't require, fish cells can live at the room temperature, and the smart idea here is apparently you can freeze the fish cell. I think I even did my research with the fish cell. You can freeze the fish cell for 6 months, for I don't know how long, and then you take them from the refrigerator. So you can put your chip in the refrigerator and freeze there the chip, and then the cells, you take the chip from the refrigerator with the fish, trout fish cells, and the chip is working. It's a bit hard to work with cells though. Okay. Now here you can see, here is the impedance value of the impedance, and here is the time, in time, you know, and the impedance is getting like that. A little bit of fluctuation because the cells are not attached totally all the time, they a little bit move there. And the impedance is a function of the cell numbers. If you have, it's better to work with a concentration, high concentration of the cells, because you will have more cells on the chip and you will have a high impedance. Okay, so this is the information from the quartz crystal microbalance. You inoculate the cell here, maybe the, this is when you introduce the cell on top of the quartz crystal microbalance. When you introduce the cell, the resonant frequency shift. This is the highest value of the resonant frequency, and then the cells start to go closer and closer and closer to the top electrode and attached to the top electrode of quartz crystal microbalance, and so the resonant frequency is a little bit less, lower value. Here, what is here? Resonant frequency shift. Yeah, here is the same idea. You have different concentration of the cells, and the highest concentration of the cell is producing the highest resonant frequency shift. If the cells are more concentrated, that means you have more cells there, you have a lot of cells, and then the cells are coming down and attaching very strongly on the substrate. And so the resonant frequency shift, because the cells are heavy, the resonant frequency shift is a bit higher. And we can see, it was very nice that we can see with the microscope, even the electrode is from gold, but it has a certain transparency, and with the microscope in the lab, we can see how the cells form a monolayer on the gold electrode. Simultaneous measurements of water toxicity using ammonia. So I think this graph is good, because in this graph you can understand how the two sensors are behaving when we introduce ammonia. So this is the resonant frequency. What happened? When you introduce ammonia, the cells are not happy, they will die, and when they die, the monolayer is detaching from the electrode and starts to float, and the resonant frequency is coming up. And then here is the impedance. The impedance is getting lower because I told you when you introduce the toxicant, the impedance is getting to 0 because the cells are dead. Here you see impedance from the highest value getting to 0, resonant frequency from the value corresponding to the cell monolayer is getting up. And these are our signals to tell us that something is in the water, but we don't know what is in the water. We don't know. Now, there is a protocol. I will not explain all the information about this protocol, but there is a protocol. The student was very, as I said, a very good student. He knew how to culture cells. He was very eager to graduate and to do good research, etc. But we cannot do this test. We never had any results till somebody told us something very interesting. When you like the cells are like us, they eat something from the nutrient, and in order for the cells to be sensitive to the ammonia, they need to be very hungry, to starve. So it was really hard. You need 5 hours before the experiment to change the media in the cells which contains the nutrient only with serum, like water. And they stay 5 hours without any food, or only with serum. They are very weak, and then you need to introduce the toxicant inside. And we introduced toxicant with different concentration, and the cells were really sensitive. And where in that moment, when you do that 5 hours into the serum and then you introduce ammonia, the cells are dying. And you can see this is before the experiment, very strong monolayer here, and then you introduce ammonia, and then very, very short time the cells are dead. And here are our results after you introduce ammonia, and of the resonant frequency. The resonant frequency is growing, is getting up, and the shift. Here is the shift of the resonant frequency. Is getting up because the cells are dead. After you introduce ammonia, they detach. They immediately detach in very short time. You can see here the time of detachment. It's like in minutes. In like 10, 20 minutes, the cells are dead and apoptotic, and same for, we were surprised that the same, of course, the same result for the impedance spectroscopy, where the impedance is getting to lower values when the cells are dead. And here you see the impedance is decreasing after the same 20 minutes. The impedance changes the values. We did many, like to have a good paper, you need many testing, and we did nicotine, and Army also asked us to do more testing to confirm that, the cells are dying, and it's the same nicotine. Apparently nicotine is in some places very high concentration in the water, and resonant frequency is increasing, impedance is decreasing. In the same, like nicotine, maybe the same toxicity like the ammonia, the time is the same almost. And then we did aldicarb, which is in insecticide, and the same results. So we were sort of successful, and at the end we published, I don't know, maybe 2 papers. We were very lucky to publish in Lab on a Chip. It's hard to publish there. We had a sensor. We had 2 sensors to check the viability of the cells. Now, what happens if the water is good? You can drink the water. The cell will die because the cell is not used to water. The cell doesn't like. The cell likes media with the nutrient or serum. But even the serum without nutrient, the cell in a certain time will die. But with water, the cell will also die, but not in 10 minutes or 20 minutes. Will die in 24 hours or 30 hours. So when you introduce water, they are still happy for a long time. So they can control. So this sensor was good for rapid screening of toxic industrial chemicals in water. Different concentration of chemicals were detected after the cells were cultured on the device for 24 hours to 48 hours. That is a bit hard to, because what happened when you go with the device to the microscope to see you go from the incubator to the microscope, and sometimes the cells are contaminated. Now, this second topic doesn't have cells. This is a modern type of research. Very many people in America are doing. So I went to a conference. There is a professor, John Roberts. He explained he has stretchable electronic. And then after I hear him with stretchable electronic for this and stretchable electronic for that, I was thinking, okay, now it's my time to try some stretchable electronic myself. It's not so easy, in fact. But it's not hard. This research I did with master degree students. So, I was lucky to have zinc oxide piezoelectric material to use for this research. So the research was based on the fact that I have a sputtering deposition of zinc oxide. And then, zinc oxide generally is deposited at 300-400 degrees Celsius. But for stretchable electronic, you need the substrate to be a polymer, and you need to go with very low temperature for sputtering of zinc oxide. So we sputter zinc oxide at room temperature. And during the sputtering process, the temperature raised maybe to 80 degrees, but didn't destroy the substrate. So the nano generator was fabricated from zinc oxide. I say nano generator because the thickness of the zinc oxide was in the nanoscale, 200 nanometers, something like that. Zinc oxide was like a thin film embedded in polymer materials. The microfabricated nano generator will be attached on the skin and stretched by the natural movements of arms, legs, or neck. So I wanted to create a battery to have zinc oxide, which is piezoelectric. When you elongate piezoelectric material or you touch, it's a pressure there, the piezoelectric material will produce a voltage. And in our case, the output energy from this device was around 200 microwatt. And we were thinking that skin sensors, like to do electrocardiogram or some type of sensors, can be powered for the stretchable battery. Now I show you the fabrication here. So we have silicon substrate, and you need to, on the silicon substrate, you need to deposit PVA. You fabricate the sensor. All the MEMS devices start with silicon, but here silicon is only the base because your sensor is from PDMS. That is the material. You fabricate the sensor on PDMS and you stretch. This is the fabricated sensor. You stretch PDMS. You can stretch. It's elastic. Not too much because you break, but a little bit. And you need to, after you fabricate, you need to detach your sensor. And for this, you need PVA. PVA is making the PDMS is a polymer and it's very strongly attached to the silicon substrate, but this PVA, it's letting the PDMS to detach. And then you deposit, we deposit gold. No, first you deposit, so you have PVA, then you have PDMS, and then you need to deposit the lower electrode. I think it's good to show you a little bit the image of the fabricated sensor. So zinc oxide, in order to be transformed in a battery or something, in order to extract, to collect the voltage, needs two electrodes, one electrode on top and one on the bottom. So you have PDMS, you fabricate gold. We have a monolayer of gold here, a layer of gold, constant. We don't require a mask for this gold. Then we spatter zinc oxide, and then we fabricate the electrodes on top with the shadow mask. We just did the shadow mask, and we spatter gold, and then we need to detach the whole device. We detach the whole device. Here is PVA, okay, which let the device to be detached. And this is the device. And very hard was to connect these very fragile electrodes on the PDMS with wires. So, but we were able to connect. And so this is the sensor. The battery is like a battery. Here is the battery. Here we develop a linear motor. And we attach the sensor on the linear motor to stretch in a very monitored way, very controlled way, just a little bit to stretch. And this is the oscilloscope to check the output voltage. Now, this is the zinc oxide when it's stretched. Very interesting. I was thinking my idea is not good and will not work because when I look at the microscope, SEM microscope, the cracks, so much cracks in the zinc oxide. Gold, also, this is the resistance of the gold layer based on the stretch. You stretch 10% or less, 6%. The resistance is less and less. So the gold is changing the resistance. I was thinking this will influence a little bit the harvesting of the energy from this device. And here is like the students, like master degree. I had a good master degree students who like to write this LabVIEW program for to stretch in a controlled manner the stretchable power generator, and here is the device source meter to record the output voltage and current. So here, maybe this is working. Oh, here I cannot use my pointers from some reason. It's okay. No, I think it's coming. Because I'm so proud of this, this is my child or something, like when we started to test and we saw on the oscilloscope the output voltage. Every time you stretch, and the device is producing an output voltage. Now, I tell you the truth. This is very fragile stuff. Maybe after COVID, recently, I wanted to redo this research. The sensor is not working. So it has a short life. I don't know how short, because after maybe 6 months or 8 months or so, I tested and it was working. And that means the piezoelectric material lost the piezoelectric properties. And some small voltage I can still see, but not here, was like 2 volt, the output voltage. And then what we did with this motor, we stretched only like 3 millimeter, not too much. And when we start stretching, we saw the power is increasing, of course, because we stretch. And then the power we cannot get more power after 3 millimeter. And we decided not to stretch more, not to destroy the sensor, because probably the cracks in the piezoelectric material were so big that the sensor was not able to produce more power. But it was nice. And in the literature, the other sensors, the other batteries or some power generator like this one, have even less than 200 microwatt. Now, what we observe here are the cycles of stretching. And we observe that if we use the different frequencies, we'll use very low frequency, because this sensor is intended to stay somewhere on your neck or here or somewhere, so the body cannot produce very high frequency. We use low frequency, and we see if the frequency is like very low, the power output is smaller, and then if you have a little bit of higher frequency, the power output is a little bit higher. And then we look also at the speed. You can stretch with a certain speed, like a little bit slow or a little bit faster, and also the highest speed will produce the highest power, but we cannot go more. Whatever we did, we wanted to get higher than 200 microwatt, we cannot. That was our, and this is my last slide. The student fabricated, the master degree students, I had many students, and everybody fabricate one, and with difference, they were thinking a different structure for the electrodes, but everything was the same. Like we test them, and we didn't get more powers than 200 microwatt. And the money came from National Science Foundation, Army Research Office, and Institute. This was my very high help for me. This Institute of Soldier Nanotechnologies, they sent me many years in a row money to do research, and they are part of Massachusetts Institute of Technology. And it was prestigious to work for them. And this research was for them. And thank you very much for listening to my talk. I hope I didn't go over 40 minutes. I speak about my student, about my stress to find idea of research and all this. Generally, people don't tell their secrets like that.
Thank you very much for your talk. Now let's see if there are some questions. ¿Alguna pregunta que tengan? Sí, por favor.
Of course.
Un momento, ahí va el micrófono.
Of course. I think we can hear his voice. Or Institute of Soldier Nanotechnology. No, this last research, which I did with the master degree students, so I didn't have the money for a PhD. They send me every year for like 4 or 5 years, $50,000. It came for them. And they are very incredibly good, like to monitor me. I need to write reports, and they like the research. They will not send me every year like blind. Every time I need to send them whatever is my progress, and they will send me 50,000. And what was good for this, I didn't give too much money to the master degree student. I used the money for buying materials and for me to travel. I was able to travel to many, many good conferences. And I was lucky because they picked me out of the blue to sponsor me, and then many years they send me money. Even for the first presentation, they send me some money. But for the first presentation, I have money also from National Science Foundation. The problem is they give you money to support the PhD student. Like I told you, the first was with the PhD student, and you support the PhD student for 1 year. And then they don't care, or 2 years. And then the student will not finish in 2 years. You know how it is. And then somehow I had a luck after this gave me the money for 2 years. Army from, but it was another Army research office, but it was somehow connected to Institute of Soldier Technology. They gave me money. They liked my research. And then the Institute of Soldier Nanotechnology gave me money for this second research. And for another research, which I didn't present, I think it's enough for what I presented. But I only want to tell you the other research was stretchable, because I was trying to do stretchable impedance spectroscopy. Like this sensor for the cells to stretch. Like you can stretch the cells and to check, you know, like for instance, you elongate the cell and you see if they multiply, they proliferate. And we see with the impedance, if they proliferate, you stretch, and you see the impedance is growing and growing and growing. This was also interesting research, but I will not finish if I start with so many topics. And for the impedance spectroscopy stretchable sensor, I had also a PhD student doing that research. And 1 second only, because Jose is curious, and I don't think I will tell him all my research. I don't know if you are familiar with surface acoustic wave. We had at GW Dr. Zagrul did surface acoustic wave. It's another type of resonator. So the last PhD student fabricated this surface acoustic wave and tried to check the viscosity or something about the liquid you drop in the acoustic path. But this research also I didn't present. But it was also sponsored by these 3 grants I'm showing you at the last slide.
¿Alguna otra pregunta? Sí, adelante.
The resonant frequency, the shift. I think this is a good question. So, how do we measure the shift? We measure, I think the shift, I think it's calculated from the resonant frequency, initial resonant frequency. I think you cannot measure the shift. You need to calculate from your initial, you know the resonant frequency, initial resonant frequency, and then you know the resonant frequency with the cells on top, and you calculate, I think. I don't think you can measure with the impedance analyzer. It's not possible to measure the shift, because you have the without cells and with cells, and the device will not be able to do this calculation for you. Yeah, I didn't think at this. But I think it's a good question. And the impedance is also normalized, and the normalization of the impedance is in the same way. You do the impedance because is without cells, and then you divide the impedance with cells and without cells, is something like that, and it's the value of impedance is like so-called normalized impedance, is not the real value of the impedance. Normalized. The impedance is like 2,000 ohm, 4,000 ohm, but here is normalized impedance. I think also by calculations. You divide one value with another value.
Muy bien, ¿algo más? Entonces le damos las gracias otra vez a la doctora.
Thank you very much.
Y se le va a entregar un reconocimiento que dice a la doctora Ioana Voiculescu por impartir la conferencia Innovative Man Sensors and Biological Applications Research and Developed
So
at the
nice.
City College of New York. And it's signed by our General Director. Firmada por el Dr. Edmundo Gutiérrez.
Thank you very much. Gracias. Thank you. Thank you. Thank you very much. I'm very pleased to, and I hope you enjoy my seminar.
Yes.
It was different from the research or the interest of everybody here, but it was some ideas. You see the struggle of other scientists to do something. Okay. Yeah, no problem. I am with, and thank you very much. You were very nice to accept me here and present me. Yeah. Yeah.
Thanks.
Have a good